Hello everyone, welcome back to online class on physics. Today we are discussing about ray optics and optical instrument, and in this lecture I am going to discuss a very important topic, that is Landsmaker formula for double or biconvex lens and double concave lens. Okay, so you can remember my previous lecture where I have already discussed about lens. What is lens? A lens is a piece of refracting medium bounded by two surfaces, and one of which must be a curved one. Okay, so lens means a piece of refracting medium bounded by two surfaces. I have already discussed the types of lens. There are two types of lens, convex and concave. So let's start the lecture. Here I am going to discuss Landsmaker formula for double convex lens. So double convex means biconvex, means the convex lens which has two surfaces and two surfaces are convex one. Okay. So here from the ray diagram you can see it is a biconvex lens of refractive medium mu2, medium of refractive index mu2. Okay. So it is a biconvex or double convex lens of refracting medium of refractive index mu2. It is placed in a medium of refractive index of mu1. Here mu1 is less than mu2. That means the medium of refractive index mu1 will be a rarer medium, and the medium of refractive index, the lens medium, will be denser medium. Okay. So here you can see that double convex lens, so it has two surfaces, convex surface. One is LP1N and other is LP2N. Two surfaces are there. For the first surface, LP1N, P1 is the pole, C1 is the center of curvature, and R1 is the radius of curvature. And for the second surface, LP2N, P2 is the pole, C2 is the center of curvature, and R2 is the radius of curvature. That means for this lens, we have two center of curvature, we have two radius of curvature, and two poles. Okay. Now, we are taking some assumption. We are assuming something here. First of all, a lens means a double convex lens means two convex surface. So it has two radius of curvature and two center of curvature. Already I have discussed. And here, the refractive index of surrounding medium and the lens materials are mu1 and mu2 respectively. Okay. Now let's start the derivation. Okay. First, from the ray diagram, we can see that two surfaces. The lens has two surfaces. So first we will consider the first surface only. Okay. First we will consider the first surface, that is LP1N surface only. Here O is the point object situated on the principal axis in front of first surface. So a ray of light OA is incident at A of first surface. Okay. Now we have to draw a normal here. So what is the normal? We know that for a spherical surface or for a spherical mirror, normal always passes through the center of curvature. So N1 C1 is your normal, and here light is traveling from rarer to denser because mu1 is less than mu2. So the medium of refractive index mu1 is the rarer medium, and the medium of refractive index mu2 is the denser medium. So light is traveling from rarer to denser. So after refraction, light will bend towards the normal. Here N1 C1 is the normal. So this light after refraction bend towards the normal. So AN is your refracted ray here. Now see, if the surface LP2N is absent, that means you can consider this ray diagram. If ray LP2N is absent, then this ray AN will meet the principal axis at I1. That means I1 will be the real image of O. For the first surface, object is O, I1 is your real image. That means if we ignore the second surface, that is LP2M, then our ray diagram becomes this one. Only one convex surface is there. Okay, in this case, O is your object, I1 is your real image. Now, let the distance of I1 from the optical center be Q1 and the object distance is U. Okay, and light is traveling from rarer to denser here. So we can use the refraction formula for convex spherical surface. What is the refraction formula for the first surface? You can remember this. In our previous lecture series, we have already discussed refraction at spherical surface. So for the first surface, your refraction formula becomes this. So you will get the first equation. Now see, but actually the second surface is present. So the ray AN will suffer another refraction. Is not it? Actually, the surface LP2N is present. So the ray AN will suffer another refraction. Now, for the second surface, AN will be the incident ray, which is directed towards I1. So I1 can be treated as virtual object for the second surface. So we can treat I1 as the virtual object for the second surface. Is it clear? For the actually second surface is present. So AN will suffer another refraction. Now second surface AN is the incident ray, and this incident ray is directed towards I1. So I1 can be treated as a virtual object for the second surface. So for the second surface, you can we can ignore the first surface and object. Okay, we can ignore the first surface. So for the second surface, the ray diagram becomes this. Okay, so here I1 is the object and light is traveling from denser to virtual object. So light is traveling here from denser to rarer. So it bends away from the normal. You can see from here. AN will suffer another refraction. That is, AN is the incident ray. At point N, we can draw the normal. And we know for spherical surface, normal always passes through center of curvature. For this surface, what is the center of curvature? C2 is the center of curvature. So N2, C2 is the normal here. And here light is traveling from denser to rarer. So after refraction, it will bend away from the normal. And Ni is the refracted ray. Here the refracted ray finally meet the principal axis at I. So I is the final image. इस लेंस से हमको O का जो इमेज दिखाई देगा वो क्या है? I is the final image. O का इमेज हमको I पे मिलेगा. So I is the final image here. And for the second surface, we can say that I1 is the object, I is the image. So P1 is your object distance and P is your image distance. And light is traveling from denser to rarer. So we can write for the second surface, we can write the refraction formula as this. Okay. Now see, we can easily add this to equation. Add this. Now, after adding, you can see mu2 by phi1 is there, having a plus sign, and mu2 by phi1 is there, having a minus sign. So these two terms will be cancelled out. So we have mu1 by phi minus mu1 by u equal to, and here we can take common mu2 minus mu1. So mu2 minus mu1 equal to 1 by r1 minus 1 by r2. Okay. Now just simplify it. Take mu1 common from left hand side and divide both sides with mu1. Then you will get equation this. It is write it equation 3. Okay. Now from if your object, that is O, is placed at infinity, then we know that if your object is placed at infinity, then image will be formed at focus. That means here the image distance will be the focal length. So in equation 3, you can put u equal to infinity. So 1 by infinity, that is 0, and p equal to focal length, that is f. So 1 by f equal to this. So it is equation 4, and it is the required Landsmaker formula. Okay, बच्चों, याद रहेगा. What is this? It is the Landsmaker formula. Now, from 3 and 4, we can compare equation 3 and 4, and you can see the right hand side equal. So you can equate the left hand side, and you will get 1 by p minus 1 by equal 1 by u equal to 1 by f. Okay. Now, another assumption is there. If your lens is placed at air, that is the refracting medium of refractive index mu1. If the refracting medium of refractive index mu1 is air, that means mu1 can be equal to 1. We know that refractive index of air is 1. So mu1 equal to 1, and we can write mu2 equal to mu. So if we write mu2 equal to mu, then our equation becomes this. Okay. So here mu is the, what is mu? Mu is the refractive index of the material, and this is the Landsmaker formula. It is the Landsmaker formula. Okay, student, is it clear? Okay. Okay, student, it is the required Landsmaker formula. Is there any problem or doubt? Now see. Limitations of the Landsmaker formula. Limitations. The lens should not be thick so that the space between the two refracting surface can be small. ये दोनों सरफेस का बीच का जो डिस्टेंस वो बहुत ज्यादा नहीं होना चाहिए. Okay. And second one is the refracting medium of both sides should be same. That means if this side में अगर AR है तो उस side में भी AR ही रहना चाहिए. Refracting medium of both sides should be same. Okay, student, is there any problem? Now we will derive the Landsmaker formula for double concave lens. So what is double concave lens? Where both surfaces are concave one. Where both surfaces are concave one. Okay. There are two surfaces are there. You can see from the ray diagram. One surface is x1 cy1. X1 p1 y1, and another surface is x2 p2 y2. Two surfaces are there, and both surfaces are concave. So it is biconcave or double concave lens. We will use similar formula, similar step, and similar assumption. Okay. Here you can see also this biconvex lens. This is placed in a refracting medium of refractive index mu1. And here a point object is situated on the principal axis, that is O is a point object here. And for this point object, a ray of light O is incident at the first surface. So when we'll consider the first surface, we can ignore the second surface. Okay, these are the steps. First, we'll consider the first surface only. And when we're considering the first surface, we can ignore the second surface. After that, we'll consider the second surface only. And in this case, we'll ignore the first surface. So for the two surface, we'll get two refraction formula. And after that, we can add this refraction formula and we can get the required Landsmaker formula. Okay, Landsmaker formula is same for both convex and concave lens. Is it clear? Now see, here the double convex concave lens, two surfaces are there, x1, p1, y1 and x2, p2, y2. And first we will consider only the first surface, that is x1, p1, y1 surface. And for this surface, O is the point object and ray of light O is incident at A. So we'll draw a normal here. Okay. And here light is traveling from refractive index of mu1 to mu2. And mu1 is less than mu2. So it is a rarer medium, it is a denser medium. So light is traveling from rarer to denser. So it will bend towards the normal. And we know that for a concave lens, for a concave refracting surface, light diverges, that is spread out. Okay, that means after refraction, we can get a virtual image, that is I1. So for the first surface, I1 is your image, O is your object. So P1 is your image distance, U is your object distance. So for the first surface, we can write the refraction formula. Now we will consider, now you can see AB is your refracted ray. For the first surface, AB is your refracted ray. But actually the second surface is present. So the ray AB will suffer another refraction. Okay. So at point B, another refraction, AB will suffer another refraction. So in this case, another virtual image, that is the final virtual image, we'll get the another virtual image, the final virtual image I. So I is the final image here, and the distance of I is P. Okay, so final image distance is P, and for the second surface, what is the image here? What is the object here? I1 is the virtual object. For the second surface, I1 is the virtual object. I'm repeating this. In order to derive Landsmaker formula, first we will consider first surface. And when we are considering the first surface, we will ignore the second surface. And first of all, for the first surface, we will get the image. And that image will serve as a virtual object for the second surface. Okay. So for the second surface, your object will be I1 and final image will be I. So P is your image distance and P1 is your object distance. So for the second surface, you will get the refraction formula as this. Now you can add these two. It's not it. You can add 1 and 2. Now adding equation 1 and 2, you will get this. Because here U1 by P1 and mu2 by P1 can be cancelled out. Is not it? Okay, now simplify it. U1 can be taken common. You can simplify this. Okay, now after simplifying, you will get equation. Now you can see this. Okay, so you can simplify this like this. Now you can say if your object is placed at infinity, that is, if your object is placed at infinity, then you will get the image at focal point, that is focus. So your image distance will be equal to the focal length. So you can put u equal to infinity. So this term will be 0 and v equal to f here. So 1 by f equal to mu 2 by mu 1 minus 1 into 1 by r1 minus 1 by r2. You will get the equation number 4. And it is the required lens maker formula for double concave lens. Okay. Now you can compare 3 and 4. You can see from equation 3 and 4, the left right hand side are equal. So you can equate the left hand side. So 1 by v equal to minus 1 by u equal to 1 by f. Again, if this lens is placed at air, then mu1 equal to 1 and mu2 can be written as mu. So in this case, you will get lens maker formula 1 by f equal to mu minus 1 into 1 by r1 minus 1 by r2. Okay. Where mu is the refractive index of the material and this is the lens maker formula. Now, what is the limitation of lens maker formula? Limitation is the lens should not be thick so that the distance between these two surfaces can be small. मतलब लेंस ज्यादा थिक नहीं होना चाहिए, ये दोनों सरफेस का बीच का जो डिस्टेंस है वो हमेशा स्मॉल रहना चाहिए. और एक है तुम्हारा इस साइड का जो रिफ्रैक्टिव इंडेक्स एंड इस साइड का रिफ्रैक्टिव इंडेक्स सेम होना चाहिए. ठीक है. सो हमारा लेंस मेकर फॉर्मूला का डेरिवेशन हो गया. Okay, student. In our next class, we will discuss thin lens formula, which is also very important for you. Okay. So, bye, student. So we can end the class. Bye.